Hi students, so this is the first in the videos for the Unit 2 Mechanics section, and I'm going to be mainly using some simulations. In the first one I'm going to be using this simulation. I'd just like to show you where I get it from. This is the site, this is the PhET site. It's a wonderful site. It's got lots of different simulations, not only for physics, but also for other subjects. There's also some math ones, or if you're taking chemistry or biology, you can use those. So it's a wonderful site, and I'm going to be using a number of these simulations. I thought I'd just tell you that. Okay, so starting with this, I'm also going to be using the notes outline. So the idea is that you can go through this with your notes outline. So we start off with this idea of defining these concepts: displacement, velocity, speed, acceleration. But I just want to remind you that we are going to be starting off with our SI units. Now, the two that we're starting off with initially are the ones for distance, which is the meter, and for time, which is the seconds. And we should always, in most cases, whenever we are given units that are not in meters per second, usually we would put them in meters and seconds in most cases. Now, this idea of displacement, I'm going to use the simulation to describe it. But before we do that, we actually have got this idea of distance, which we measure in meters, as has been stated here. Now, displacement is a build-up on distance. It's distance in a specific direction, basically. Distance traveled in a particular direction. It's what we call a vector. It has both magnitude and direction, where distance is a scalar. It only has magnitude. It only will have distance. But it will only have meters, for instance. But with displacement, you also need to give a direction for it. So, just to explain the difference of those, I just want to call up this simulation here, and we're going to be using this over here. This is a very funny thing, and I'm just going to be going a little path here and then bringing it to an end. Okay, so this ladybug has traveled a certain distance. Now, this whole length here, if we took a trundle wheel and we measured all the way around here, that would be the distance that the ladybug has traveled, and that would be given in meters. But the displacement is from the beginning to the end point. That over there would be the displacement. So this all the way around is your distance. So this is distance all the way around. This is your displacement here. So basically it's the final position minus the initial position. We denote it with the symbol S in the IB curriculum. Distance, we use D, sometimes we just use distance, DIST, or so forth. Now, when we look at the time, when you divide this by the time that it took for this, when I take S divided by T, the change in displacement over the change in time, I get velocity. And a velocity convert is also a vector. But when I take my distance over my time, I get speed. So speed, when we are dealing with this in physics, we always look at speed as distance over time. It's a scalar, where velocity, which is displacement over time, is a vector. Now, I can actually point this out. Let's just clear this data here, and I'm going to start this ladybug offer again. Now, if you notice that velocity vector, see, it gets big, gets small, but it's giving a direction. Now, that's the velocity that is going. We'll come to the acceleration a bit later. So, right the way along, this this over here, this direction, is giving the velocity in a specific direction. Again, here, if I wanted to measure the speed, I would have to take the whole path. I'd have to measure that whole path. I'll get the distance and I'll divide it by the time. If I wanted to take the velocity, I've got to go from where I start to where I end. I've got to have that is my displacement. We give it the symbol S, and its velocity is equal to S over t, the change in S over the change in t. Okay, I hope that helps in explaining the difference between speed and velocity. Now, as you've noticed here, as I've been doing this, I'm going to just show something called the acceleration vector. Now, the acceleration is to do with the rate of change of velocity. So here I'm going to start my ladybug off again, and I'm going to accelerate. And you can see there that we have an acceleration vector. Now, this is this acceleration, we use a symbol A, is equal to the change in velocity over the change in time. So going back to our SI units then, we know that our velocity, which is equal to our change in displacement over our change in time, that is a meter divided by a second. We denote velocity and speed, both of them, the magnitude of them, as a meter per second. Now please, if you can write it like this is correct. We don't use this, we don't do this in the IB curriculum. So we use that to the velocity in terms of your SI units is a meters per second, where your acceleration is equal to your change in velocity over change in time. That is a meter per second divided by another second. So your unit for acceleration is a meters per second to the -2. Again, we don't write it like that. That is not how we write it in the IB curriculum. So going back here to our notes, we have defined these things. So I've got the definitions here. The rate of change of velocity, the rate of change of distance is speed, the rate of change of displacement is velocity. And here we have the distance traveled in a particular direction. So we have those. Just this point here, explain the difference between instantaneous and average values. If something is done in an instant, where this word instantaneous comes, it's over a very short period of time. So the instantaneous velocity, I'll just shorten like the instantaneous velocity is the velocity that is done over a very short period of time. We'll look at this when we are looking at graphs in more detail, where your average values are taken over a period of time. So you may go traveling, you may travel from A to B, maybe it's 200 kilometers and it took you 2 hours. Your average velocity, and we often denote it like this, would equal 200 kilometers divided by 2. That will be 100 kilometers per hour. This would be an average value. But on the way, when you're traveling and you look at the odometer or the speedometer or whatever you'd like to call it, as you're traveling at a certain instant, you look at it and you see, okay, you were maybe traveling at this point, you were traveling at 130 kilometers per hour. But at this point, you had to really slow down and there was a traffic jam and so forth. You maybe were traveling at 60 kilometers per hour there. So you would get a change, but at each point, those would be your instantaneous velocities. We just to finish this off, outline the conditions under which the equations of motion for uniformly accelerated motion may be applied. This is when you have a constant g, and so it's a constant a or a constant acceleration. G is for this over here when it's falling under the influence of gravity, Earth's gravity, it's g. So when you've got a constant acceleration, a uniform acceleration motion, we have the equations of motion. I'll be showing those in the next video. So that's it for the moment. Perhaps I can just show one last thing with the simulation, just to show us what we're going to be mainly discussing is motion in a straight line. So let me get this ladybug going directly across. We're going to be discussing motion mainly in a straight line, where you go in that direction at a constant acceleration. That's mainly what we're going to be dealing with in this section. Okay, thank you very much.